Hello students, and particularly seekers of general truths. In this video, we will look at another example of how we can apply the definite integral, or at least the approximation of the definite integral, to understanding a variety of problems. And in this case, a problem with two conflicting rates. Okay, so water is pumped into a tank at a rate of 8 gallons per minute, and water leaks out of the tank at a rate of root T plus 1 gallons per minute for the first 2 hours. At time T equals 0, the tank contains 30 gallons of water. Okay, so let's try to imagine maybe how this looks like. So let's see here, you have a tank of water. Okay, I'm drawing this as though it was a cup, but let's say I have a tank of water, and there's some water in here, and there is water that's being pumped into the tank. So I kind of imagine like a nozzle, and then there's water that's flowing into the tank. Water flowing into the tank, and that is a rate. Okay, this is a rate of 8 gallons per minute. Now at the same time, there's like a hole here, and then there's water coming out as well. And water is coming out at a rate of the square root of t plus 1. Okay, so this rate is ever changing. So let's say that t, when t is 3, the rate would be square root of 3 plus 1. Okay, so hopefully that gives you a sense of what is exactly going on in this problem now. All right, so let's get to the work here. Using a Riemann sum of 3 equal subinterval, estimate how many gallons of water leak out of the tank between 0 and 3 minutes. Okay? So let's see how this, I like to draw the graph whenever I'm estimating a Riemann sum, because that helps me to visualize and imagine exactly what's going on here. So we want to see water leaking out of the tank. And this function here, the square root of t plus 1, that's the square root function, shifted 1 unit to the left. So it will look something like this. Okay. And again, this is at negative 1 here, and this is t. And I guess I'll call this function L of t here. So we'll call this here L of t for leaking. Okay. So this is L of t is equal to root t plus 1. And we want to estimate between 0 and 3 minutes. Okay, so let's just say that's about there. Okay. And we want to use 3 equal subintervals. So each of the intervals is going to be 1 unit, since it's going from 0 to 3 equal intervals. And we want to see how much the water leaks out of the tank. So how many gallons, right? So we start out with gallons per minute, and we want to, with a rate, and we want to compute the raw amount of gallons. So that means we're going to have to take the area. Okay, so the answer to number 1 is really the integral from 0 to 3 of L of t dt. Right? So it's really this area here under the curve between 0 and 3. But we don't know how to do that exactly yet. So for now, this is the left Riemann sum. Right? With 3 equal rectangles. So we're going to go from the left side, make ourselves a rectangle. Start from the left side here, make ourselves a rectangle. So that's the second rectangle. And then start here, make ourselves a rectangle. So one of the nice things about this is that all 3 of the rectangles have a base of 1, and we just need to figure out the height. So this definite integral is approximately equal to, and I'll just do the work here, 1 times, right? So this is the width of all these rectangles, all equal to 1. You just got to figure out the height. Well, the height is going to be, this is going to be the first height. This line right here is going to be the first height. Well, that's L of 0. This line right here is going to be the second height, or the height of the second rectangle. So that's L of 1. And then this third line segment right here, that's going to be the third, or the height of the third rectangle. So that's L of 2. And let's put this all together and actually compute the values now, or as best as we can. Right? So this is 1, L of 0 is going to be the square root of 1, so that's just 1. L of 2 is going to be, or L of 1 rather, is going to be the square root of 1 plus 1, or the square root of 2. And then L of 2 is going to be the square root of 2 plus 1, so that's going to be the square root of 3. So that right there is what's going to give us the approximate area underneath the curve, which will tell us the approximate amount of water. Okay, so this is working for an amount of water that leaks out of the tank between 0 and 3 minutes. Alright, so when I did that on my calculator, I got approximately 4.146 gallons. Okay? Approximately. And you can see that the exact answer is probably going to be a little bit bigger than this. Okay? But at least that addresses number 1. Alright, let's go on and let's look at the next problem. Estimate how many gallons of water are in the tank at time equals 3 minutes. So to compute this answer, let's just set up the functions and the placeholders. And so the amount at 3 minutes, the amount of water at 3 minutes, is equal to the initial amount of water plus the amount pumped into the tank okay, so it's like this amount, how many gallons flowed into the tank, plus, or not plus, excuse me, minus the amount that flowed out of the tank, the amount that leaked out. Okay, all right, so whatever amount was in there before, plus the amount that flowed in, and this is all between 0 and 3 minutes, minus the amount that leaked out. Okay, well, let's see how this works. The initial amount was 30 gallons of water. Plus the amount that was pumped into the tank. Now this we haven't calculated yet, but if we go back to our work here, or our just brief picture here, the water is pumping in at 8 gallons per minute, and we're doing this for 3 minutes. So 8 gallons per minute times 3 minutes will give us the amount that pumped into the tank. And the amount, and the amount that leaked out was equal to this, right? This is what we approximately what we calculated in number 1. So minus 1, or 4.46. Okay, so this ends up being 30 and 24 is 54 minus 4.146. So type that into a calculator, 54 minus 4.146, and I get 49.854. 49.854. And our units here are gallons. Okay. So this 8 times 3 here is also a definite integral. Let me just talk a little bit about that. That the amount that flowed in, so I'll call this P of T, the amount that was pumped in, right, is fairly simple. The amount that is pumped in is always 8 gallons per minute, And this 8 times 3 here, what we're really doing here is calculating the area beneath the curve of P of T, the amount that was pumped into the tank. Okay, so the initial amount minus the amount that was pumped in, plus the amount that was pumped in, minus the amount that was pumped, that leaked out, equals the amount of gallons that is in the tank at that particular time. Okay. Lastly, at what time does the tank have the maximum amount of water? Okay, and this is a tricky question. We want to know, when does the tank have them, at what time, right? We don't need to know the maximum amount of water. We just need to know at what time. So, water is flowing in, water is flowing out. Well, when does the tank have the most amount of water? Well, to understand this problem, we need to analyze the graph of the two functions here. So, and again, these functions that we're talking about here are rates. Okay. So the first function that we discussed was the amount of water that flowed into the tank. So that is pumped into the tank. Okay, so this is P of T, and we know that it's always going to be equal to 8 because it's always the pumping in is always flowing at 8 gallons per minute. That's P of T. The other function is a little bit trickier. L of T is the amount that leaked out. Okay. But you see that the amount that leaked out takes a very long time. It takes a very, very long time to grow, but it does grow eventually. So this is L of T. And remember that L of T was equal to the square root of T plus 1. Okay. And you can see here that at the intersection point, so before the intersection point, L of T is less than P of T. So when L of T is less than P of T, the amount of water is decreasing. Right? The amount of water is decreasing. So again, going back to the picture, if the amount that is flowing out, the amount of water is increasing. Sorry, during that time, hold on. If the leak is less than the pumping in, then the amount is increasing. Excuse me. So let's revisit this. So if the amount that's flowing out here is smaller, or the rate at which the water is flowing out here is smaller than the rate at which the water is flowing in, then the amount of water is increasing. Conversely, if L of T is greater than P of T, okay, then that means the amount of water is decreasing. Well, you can see here from our graph that between 0 and whatever time this is, L of T is less than P of T, so the amount of water is increasing. And then after that, the amount of water must be decreasing. So therefore, at this point, right, at this point is when the amount of water in the tank is at its absolute maximum. And to calculate that point, we can solve a fairly simple algebra problem. We can just set P of T equal to L of T, so 8 is equal to the square root of T plus 1. And solve for T, so square both sides, you get 64 equals T plus 1. Subtract 1 from both sides, and we get that 63 is equal to T. Okay. So at about at about exactly 63 minutes, the amount of water in the tank is at its absolute maximum, because after that, the leaking rate is greater than the incoming rate. Okay, so when the thing that's going out is going out faster than what's coming in, then the amount that's in there is decreasing, okay, the amount of water in the tank. So there you have it, and another example of an application of the definite integral. Just looking at the interplay of two rates this time. And the big takeaway from here is understanding the context and the units of the problem. As always, keep working hard. Thank you for watching, and have